Hi, this is Andrew from the University of Connecticut. Today I'll be talking about hydrophobic porous membranes, specifically polytetrafluoroethylene. The paper that I based my presentation on is called Temperature, Polarization, and Mass Transport through Hydrophobic Porous Membranes. First I'll talk about the composition and physical properties of PTFE, a brief history, the synthesis, more specifically polymerization, function, and applications. Each carbon in polytetrafluoroethylene forms a sigma bond with 2 carbons and 2 fluorines. Fluorine's high electronegativity gives the polymer a low susceptibility to London dispersion forces, also called van der Waals forces. In 1938, Roy Plunkett accidentally discovered PTFE, the tetrafluoroethylene gas he created for use as a refrigerant polymerized into a white powder. By 1944, Kinetic Chemicals patented the substance and registered the trademark Teflon. Free radical polymerization occurs in 3 steps. Initiation is when the free radical causes the TFE molecule to lose its pi bond and create a sigma bond with a carbon atom. This process continues in propagation, with each new TFE molecule attaching to the polymer becoming the free radical. The first 2 steps of polymerization are illustrated here. Notice the equation for Gibbs free energy, where the change in Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. When temperature gets big enough, the change in Gibbs free energy becomes negative, meaning the reaction is spontaneous and polymerization goes to completion. The last stage of free radical vinyl polymerization is termination, where the 2 carbon atoms at each end form a pi bond with a second to last carbon, creating a tetrafluoroethylene group. The lack of London dispersion forces makes it hard for both hydrophilic and hydrophobic molecules to adhere to its surface, making it the perfect material for non-stick coating on pots and pans. Its low reactivity also makes it well suited for lining pipes containing reactive or corrosive substances. PTFE is also used to line containers that carry nuclear waste. A relatively new area of study is the semipermeability properties of PTFE when it has undergone emulsion polymerization. TFE monomers are suspended inside a soap micelle, a type of bubble, with a hydrophobic inside and a hydrophilic outside. The TFE polymerizes inside the micelles, creating congregations of PTFE. The micelles join together, creating one large micelle. This allows the nodes to polymerize together in the form of fibrils. The contrast between fibrils and nodes gives emulsion polymerized PTFE its semipermeable properties. One of the most financially successful applications of PTFE's semipermeable properties is high-performance outerwear, specifically Gore-Tex. Gore-Tex's PTFE membrane makes it a unique piece of outerwear because it's waterproof yet breathable. This is a large contrast between non-breathable rain jackets and shells made of sewn nylon with a durable water-repellent coat, also called a DWR. The PTFE keeps the user dry in a downpour by keeping water on the outside and allowing water vapor to escape through the porous membrane. The pore size is a staggering 20,000 times smaller than a water droplet. Gore-Tex's target users are hikers, mountaineers, skiers, cyclists, and other athletes who want to maximize comfort in less than optimal conditions. Here is a simple diagram that I made to show the thermochemistry behind Gore-Tex. The equation is for flux. Flux is the amount that flows through a unit area per unit time. As you can see from the equation, flux is equal to a constant C, unique to the material, times the difference in partial pressures on each side of the membrane. When warm, moist air is next to the skin, and cold air, which holds less moisture than warm air, and thus has a lower partial pressure, is on the outside of the membrane, mass transport occurs. Most of PTFE's applications have to do with some form of osmosis. In the future, fresh water could become scarce. A specialized PTFE membrane to desalinate seawater for drinking water could be the answer to that problem. Other applications of PTFE's special properties include wastewater treatment and separation of alcohol and water solutions. PTFE membranes made specifically for a certain osmotic process could someday make distillation obsolete. A great deal of energy is needed to boil water for distillation. If chemical engineers could design a more cost-effective way to manufacture PTFE membranes, we could reduce carbon emissions and also have a sustainable source of drinking water as the Earth's population grows exponentially. In conclusion, I've discussed PTFE's chemical structure and characteristics, Roy Plunkett's accidental discovery of the polymer called Teflon, free radical polymerization as well as emulsion free radical polymerization. I've discussed PTFE's various applications from nonstick pans to high-performance rain jackets. I've also discussed how chemical engineers can move forward with respect to PFE membranes to create a source of sustainable drinking water. And thank you for your time. Here's my works cited. And are there any questions?